All right. So, okay, introduction, and I was here. Um, where were we? So, applications of those non-imaging optics includes lighting, illumination, LED, automotive display, and most importantly, the solar. So, if I have time, I will go through some solar tracking examples, so you guys can later install these programs yourself and use it to your advantage. And the image right there in the left is actually the example where you have a bunch of mirrors, which is focusing the solar energy to the tower, and then uses the heat to generate electricity. Um, so today I won't spend a lot of time just going through background. I'll spend most of the time to do demos. I prepared three demos. One that is light pipe, the most simplistic demo that will show you guys how the software just in general works. And second, the solar concentrator demo. I hope I can finish the solar concentrator demo on time today, which will show you optimization and utility libraries and different libraries of optics that you can put into without making your own models, which is really helpful. If I have time later, I'll cover my own project, cannula imaging, where light tools are used not only in those common applications, but more toward research side of things. Also, the limitations why light tools are not quite widely used for imaging. Um, so let's then go ahead and open LightTools. That's how their icon looks like. So if you're familiar with using Excel and window application, this should look quite familiar. They look a little bit outdated by now. They don't have a fancy ribbons and stuff, but they kind of stick to the old Windows 8, 98 sort of a theme, XP theme. So I want to start from um, opening an existing model, which will give us some sort of a starting point to cover basic things. Um, so the first thing that you see is that there are a couple of different windows. So the center one, like a CAD software, SolidWorks, you have the model view, where you can just do different mouse controls to see different views and interact sort of individually with the model. In the left, you have a navigator. So LabVIEW, one inconvenient feature of LabVIEW is that you cannot select a whole thing from this GUI. You always select a surface. That's how it's constructed in a weird manner. So in order to select the whole thing, this L-shaped cube, you have to come here and select this button. For example, when you want to change their material or like a governing property of the whole cube. So this is really useful. You'll come back here very, very often to select the specific item that you want to select. At the top, there are common common items that you can see from other design softwares. There are zoomed features, and there are different way of viewing things. You can have 4 panels and 1 panel. I prefer 1 panel, so we'll stick with 1 panel view from now on. And you can also sort of do a projection on a particular plane and fit it into the window so you can have a better shot. All of these things you can play with yourself and learn pretty quickly. And on your right is sort of a core of where the core of MATLAB feature lies. So here there's elements. Here you can create different optical elements, such as lenses and mirrors. They have a bunch of sort of predefined way of making optical elements, such as lenses, which I'll show in a later example. Mirrors as well. Some of the mirrors are pretty specific, and you won't likely be using all of those. Sure.
Just have a quick question. So, is it gonna have a screen video shot, like a video recording, or just a voice?
Yes, that's what I just did at the very beginning. So I recorded I'll be recording this whole lecture and give it to Dr. Menu so he can post it to his YouTube channel.
Because most of us haven't got a chance to download the LightTools yet. So
yes.
It's a little bit harder to track.
So do you guys know like how? I mean, was there any instructions of how to get the LightTools yet? Like I thought there was instructions or email that you can send to get the license.
They just wanted us to give him, or the instructor just wanted us to give him our UNID, but that was about it.
No, we have to go send them an email.
Okay. Yeah, that's what I did as well. I mean, I also use this student license here for the lecture purpose. So I had to give them an email and have Dr. Menon to send them an email so they confirm and send you the license file. Yeah, I don't think my license will work in any of your computers because licenses are PC specific. Very inconvenient, but that's how they protect their intellectual property. So yes, this will be recorded and you can follow step by step. And in the end, I will also give you ways to find tutorials and resources so you can follow different examples without necessarily me showing you. So there are a lot of buttons and features that there are that you don't necessarily are going to use. So here I'll be touching on like some of the basic and simple features for you to get started. So the one thing that I want to start from is within ray tracing category, there is what's called NS ray trace. It is short for non-sequential ray trace. So within the LightTools, there are two kind of modes of ray tracing. One that is sort of a drafty, rough, quick way of ray tracing, and one that's formal and sort of takes more like information concentrated way of ray tracing to do quantitative analysis. So NS tracing is the one that's rough, one that does the quick demo, like a real-time monitoring of the ray behavior. So what I want to do, okay, so a little bit of background on the model we have loaded up in there. So that's L-shaped cube made with polycarbonate, so basically plastic. And people use those kinds of structure to bring a light source from one place to another. It's really simple. So we'll be having a light source placed here. And what we want for this pipe to do is to bring the light to this plane. It's really simple. So to mimic that light behavior, what I'm going to do is to put a NS ray tracing source in front of this face. And to make it easier for all of you, at the very bottom, right here, there's a XYZ coordinates, so we can all be in the same place. So I'm gonna put this ray source at x 0, 0, negative 0.5. And what I do is I define the fan of angles that this ray will be emitted. So I'll start from the very top and finish clicking at the bottom, and you immediately see the effects of rays within, and how the rays are reflected within the light pipe. But as you see, unfortunately though, I just told you that what we want to see is ray to reflected up and be emitted to this face, but it's actually not doing that. So through this demo I'm gonna do is to bring the rays, change the structure so that the rays will actually come up instead of to the side. 1 second. I'll just have my notes so I don't forget to cover anything. First thing that I want to do is to... So do you guys have any idea? I just want to hear from you. What do you think you have to do to bring the rays up? Any opinions?
up more, so they bounce. They hit at a higher angle up, and then can travel upwards.
So you're essentially saying to make a cut over here so that we have a slanted angle over here. That's exactly what we're going to do. In fact, a lot of rays have a smooth sort of a curve on the edge, but it's a little bit difficult to do in practice. So I'm going to make a cut that'll create a slanted edge, so we can send the rays to up. And ways to do it is by clicking, going to modifying function, and oops. Oh, here. What is it called? 3D editing. So in 3D editing, because we've selected the cube, there's options that are enabled are highlighted, and the feature we are going to use is trim solid, and click this button, and it says right here in the icon 1 and 2, right? That means you're going to require, this is going to require 2 inputs to perform the trimming solid operation. So first point I'm going to select is the intersection. So one of the lines that you the point along the line that you want to draw. So if I click a point here, it's going to show a line. And what this line shows is a normal to the vector that's going to intersect the point that I just picked. So if I draw a line like this, it's going to create a cut like this. We have a marker. So you can imagine how the vector, essentially a vector that's going like this, is created by defining one point and a line that's normal to that point. So now you're seeing that some of the rays that's going up and some of the rays still that are leaking. Up to this point, things are pretty simple, and this is sort of a job that you'd be doing, optimizing your geometry in order to get whatever desired functions. But what can you do further is to sort of play with small parameters to optimize your what do you call it? The performance of your device. So to send as much light as possible to the upper face, what you can do is to come here under the cube. Again, System Navigator will help you a lot to select specific things. So come here to System Navigator, open up the cube menu, which then includes what's called plane primitive. This is the plane that's created by the trim solid operation, because we have now additional plane that has to be defined. This is now included under the cube 1 geometry. And if you double click this, it's going to pop up the properties that's related to this particular plane, primitive plane. And within it, there are right here x, y, z, alpha, beta, gamma angles. And as you see, x0 and y0, z0 is just location of this first intersection, and alpha, beta, gamma is the angle that the angle of the normal that we defined when we are drawing the second line. So by changing, say for example, y location of this first point, we can affect how the light is bounced off of the surface. Let me do a little bit more exciting thing. Let's change it to 145. And now it's clearly seen that the rays are bounced off a little bit better off the surface and sent to the top upper face a little bit better. Another, of course, parameter you can play with is the y and z. Z is the along left and right, and y is top and bottom. So if I can move my z, I guess I want to move it to a little bit left to bring more light up, right? Say to 6.5. I think this is creating a little bit better device than before. So this kind of back and forth is kind of crucial and what LightTools are providing really well. I think I ended up setting it to 6 to make my device work really well, and 145-degree angle for the alpha. So we don't have to spend much time to optimize the design, but this kind of back and forth operation we just did was sort of a point of having this NS race, because without it, what we ended up doing is we change the geometry and run full simulation and check the data. Again, change the geometry and run the simulation, and again go to the plot of whatever to kind of do this back and forth optimization. So having this NS ray really helps. So I encourage you to produce those rays on your own example when you're making your own device. But there's a limitation, of course. We can take a look at what the rays are doing, but there are not a lot of them, and it's hard to know where exactly the rays landed. So to get that more full information of the rays, we need to do the actual simulation. So this is a simulation, ray tracing, but it's very crude. To do that, you need 2 additional things on top of your structure. You need to define a source, and you need to define a receiver. So now you don't need those rays. I'm going to just come back here, right-click, and hide for a moment. Okay, so it goes away. Oops. Okay. And what's right now hidden is, if you go to View and View Preference, so in this model that I loaded, it already contains the receiver and source defined in order to kind of save time for us. If you go to Layer, there's a Loom object, short for Illumination object. And then it shows called the plane here, the arrow called My Receiver, and this ball thingy, which is essentially a source that's emitting light. I'll show later how to add your own custom receivers and sources. But at this point, you're actually set for running a full scale simulation. And then you go to Ray Trace, Simulation Input, which then shows a bunch of options, but you don't have to worry too much about those tabs. Just click, make sure that for simulation is enabled, and you will play with this number a lot, total rays to trace. So of course, the more rays you have, more accurate your simulation will be, less accurate. In this particular one, we have 10,000 defined as default, and I'm going to enable show preview rays, and I'm going to show 100 rays as an example to preview how the rays have behaved. Okay, and then you click this button, Run Begin All Simulation. And within less than a second, everything popped up, and you can see the rays is essentially behaving the same way as we have been monitoring using the non-sequential ray tracing. Okay, but the final result you're getting is quite different, because with the formal ray tracing done, what you can see now is the analysis of the data. If you go to analysis here, there are a bunch of tabs again, but you'll only be using luminescent display. And within it, there's still, again, a lot of those data, a lot of those options, but just focus on, again, what you'll be ended up using a lot will be raster chart and scatter chart. So just remember these 2 options. You can play with it and see how the other chart will look like, but there will be just main things that you'll be playing with. So scatter chart shows essentially where the ray went. So ray went as a dot. So it's a scatter of dots that represent the rays. Raster chart is more interesting because it's more of a traditional sort of a intensity graph, intensity image you'll be seeing in a lot of non-imaging imaging applications. So this will divide your plane receiver into different bins, X and Y, and just plot, do the color coding based on how many rays that has landed to a particular bin. So as you can see here, the white part is where the brightest portion is, bright part is, and red, of course, is, as the graph suggests, are the darkest part. So with the device we've created, we see that it's not that great. It reflects a lot of ray up, but it also focuses them too much. So it's not very good if you want a uniform illumination on the top of the surface. Oops. I have to make a note here on top of that. Okay. Which is about binning. So ray tracing is essentially tracing the ray and counting the number of rays where it landed. That's the essential part of what LightTools is all about. But in doing so, when you're making this illumination plot, if you go to Illumination Manager, Receiver List, Receiver for simulation, this could be a little bit tricky, but finding where it is. But I'm recording the video, so please get back and see how you find this illumination mesh object. If you double click, it pops a property window, which will then gives you a lot of control of the receiver. Then go to the second tab, which is mesh results. You see how the error estimate is 12% and 21%. These are the statistical measure measured at the peak bin, where bin that has seen the most amount of rays, and the average, essentially average over the multiple bins. One way to reduce the error is to reduce the bins. If you reduce the number of bins, then the amount of ray you will see per each bin will go up, hence better accuracy. But then let me just give it a shot and try to reduce the number of bins. And your mesh results went up. Your error now is drastically lower. But the image you're seeing is very crappy. So there's that trade-off. You always have that trade-off that you have to pick and choose. The other trade-off you also have to choose is the time. Because another way of getting a good resolution and good accuracy is to increase the number of rays dramatically up. Let me show you an example. So let me go back to, say, 9 and 15. And even further, why don't we try 18? No, say 30 and 50. So as you see, the image you're seeing is very, very noisy. It doesn't really make sense. You see that there are more rays in the center, and it goes down as it goes away from it. But the mesh results suggest that the error that you're seeing here is very, very high. So it's likely that the data you're getting out of it is not accurate. And the easy fix, I call it an easy fix because it's conceptually easy, is to increase the number of total rays. Run it again. It takes more time, of course, because now you're running 10 times more ray simulation. But if you plot the result, it's much more accurate. And again, if you go back and look at the mesh result, error rate is drastically lower. So have those in mind when you're running a simulation. Okay, I think I covered that. We have plenty of time. So I mentioned before I run the simulation that you have to have three things. You have to have your model, which interacts with light, receiver that sees the lights at a particular plane or all around the place, and source where the light is emitted. So you are essentially doing that. You're essentially defining where the light comes out of it, goes through, and where it ends up in. And the way you define a source is by clicking Ray Trace and Source. Here there are two types of source. I usually go for surface source for the simplest things. And the one that is defined over here, if you zoom in, is a point source. It's a point, oops. It's a point of light source that emits across entire emission angle, part of which ends up being in the light pipe we've designed. The way you create it is really simple. This is part of the reason why I wanted to cover it later. Click it, click it. So that's how you create a point source. And you'll end up seeing that the now light is emitted from 2 points. The reason why the pattern of lights emitted from these two sources are different is because if you double click at the source you just created, the angle of emittance or aim sphere is very different. So if you change this to, say, 10 degree, the emittance angle has decreased a lot, and it is not now emitting all over the place. It's aiming at particular angle of rays and shooting it to that. And along with the sources, there's also a receiver option. The one way I can show you very easily is by removing the current receiver. So right now, receiver is set at the sort of this virtual plane that's floating on top of our plastic device, right? So to demonstrate how to add a receiver, let me show you. Let me just delete this air lens. This is what the object is called. Just deleting it. So now you don't have receiver anymore. See how this simulation button is now disabled. Now they have no idea how to capture the information. Hence, you can't run it. Let me change the render mode a little bit to make it a little bit easier to see. Okay, so this is how the object is looked. Just click receiver and say select receiver and click at the top surface. Now the top surface becomes your receiver. So it's really similar as the previous model where you define separate plane a little bit above the top surface and use it as receiver, or this really serves the same function. But it's important, of course, how well you define your receiver, as close to your actual model. If you want to actually measure what the light intensity is above, it is important to have that gap. And because you define your receiver, you'll be able to see your raster chart and look at how it's different from previous model. The reason in this case why it looks a little bit different is because of total internal reflection that's happening at the surface of the device. So in this particular case, it was correct to have another surface that's right above your device because some of the rays are hitting the surface at the very top and reflected back. So in order to measure the light that's actually escaping the device, you want to find another surface on top of the device and use it as a receiver. Make sense? Any questions so far? I know I've kind of gone through very quickly without stopping or pausing. So anything confusing or questions? Yes? No? You guys are good? Do you think it's quite easy to follow? Straightforward? All right. Yeah, you just have to remember to put source, structure, and receiver when you're beginning the simulation. That, from the very opening of the software, isn't very clear. What enables the simulation, the functioning of the actual ray tracing. All right. So now we're done. So just a general question: what do you guys think we can do better in order to increase the output of the this light pipe, or to homologize. What's the form? Unified. Make a uniform illumination on top of the surface. Do you guys have any suggestions? What can we do different?
To make it level on the top.
To have uniform light intensity. So right now, if you look at intensity, I should say luminance. Oops. It's quite focused on the top portion of the surface. What can we do to make it homogeneous? Suggestions? No? One thing I can quickly show is, so if you go to this plane in right here, have plane, right click optical property, you can change the optical property of one specific plane. And one thing you can do is to add a scattering medium instead of reflecting medium. Let's see what happens then. Okay, I'm gonna call it white paint and make it a simple scattering surface. It's analogous to a white paint. It reflects, but it reflects in a random direction. I just apply it. Oops, do a simulation again. And you see how random it got compared to the last simulation. And if I look at now the raster chart, it's very homogeneous. Right? On the flip side, though, the power has gotten reduced drastically. You're not seeing as much as light at the top surface anymore because a large portion of it gets escaping the device as a result of random scattering. So those are kind of optical designing thinking that you can do when you're making your own devices. So are you guys, when you're doing project, I think you have to show some kind of simulation or design work on your own. Is there anybody who's doing solar as their project?
I think we all are.
You guys are all?
It's all solar based.
So every team are doing solar projects. Okay. Then the next part becomes very important. Okay, let me show you then how you can simulate a solar cell in not just at one particular location of the sun, but throughout the day, throughout the year. Okay, let me close this model. Oops. We don't want to save it. And start a brand new model. So what we've just went through is what's called core LabVIEW modules. So we've done the basic ray tracing. We've tested with basic ray tracing features, but what they've added on top of that is what's called utility library. So if you come to tools, there are display film library, example model library, LED library, blah, 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 that really adds strong design capability of the LightTools. Without it, really it's just ray tracing device. So what we want to do is to go to utility library. That's tiny. Can you read them? No? Yes? It says right here, second from the bottom says solar tools. There's two options, one solar tracker, two solar source. We're going to use solar source, but you guys are welcome to dig into solar tracker because they are really much stronger, much powerful tool to devise a solar concentrator or solar system. But we'll stick with simpler solar source and build our demo around it. So this will give us this simple, a little bit complex window. I'm gonna go through individual features and what it does. So solar source utility will help us build a source that's simulating a sun, a cell that's simulating solar cell, and tracking, an automatic tracking ability throughout the day. Not throughout the season though, throughout the day, from 12 a.m. to 12 p.m. 12 a.m. to 12 a.m. So what we want to do very first is to set variables to LightTools, just right here. You can, by the way, change the location of where you are, and then it changes the solar insolation data set, which then affects the amount of energy that hits your solar cell. But I'll just stick to Phoenix. It's close enough. I don't think we have to worry too much about solar insolation at this point. So just click Set Variables to LightTools, and it's going to just set these different parameters. You don't have to worry too much about the details here. And make sure you enable this toolbar setup. It's helpful in many cases. I sometimes come here to do, say, to change the view. I'll just go back and forth between these two windows. The first thing you want to do is to make a sun source. Okay, it says sun source. If you click this button, it's going to create a solar source with all the different default parameters. If you want to change anything, come here and click Other Options. This Other Options will essentially govern how your source will gonna work, how your cell's gonna work, and etc. So I'm gonna just create the basic default sun source. Click. It's gonna give you a warning, but ignore and click OK. And wait a couple of seconds until LightTools does its thing. Come back. I have to minimize this. And you'll see this. In order to see the big picture, I'm going to click Fit. Oops. So what happens is they've defined a surface source as a sun that's very, very far away. That far away essentially simulates how the sun is illuminating the Earth. And this circle is not Earth, but it's the sky that surrounds your solar cell. That's what simulates this diffusing effect of your sky, atmosphere, and cloud. At this point, we are not interested in diffuse day or diffuse sky very much, so we're gonna hide it. So come here, right-click, hide. It's gonna give us better view of our device. Come back to Solar Source Utility. I really like this button, User View Second, because, oops, where did it go? And zoom. So if you zoom in, so it says zoom to diffuse source aim area, and click 2. It's going to give you a good view, a good zoomed in view of your actual area of interest, not the whole thing. Next thing you want to do is to put a solar cell. So the warning just said everything in here is in the unit of meter. And 1 meter cell doesn't really make a lot of sense, so I'm going to make it a little bit smaller. What about 5 centimeter? Let's make it 10 centimeter cell. Okay. Set it, make a cell. Okay. Now the yellow thing at the center is the cell you have. Okay. Now you're pretty much done, because when you define your source, you've defined the source. When you define the cell, you've defined your receiver. And your optical material really is just free space. That's basically what you're simulating, right? And at this point, if you click Begin All Simulation, you end up in simulating the ray tracing, and you can do the raster chart. And this exactly represents what I told you when I said the issue of undersampling or binning. I think right now the binning for this particular cell is, so here come to the receiver and open the 4 simulation and double click luminance. It is 17 by 17. If you're interested in spatial distribution of delay rays, having those are good, but because we're interested in the power, amount of rays that we're collecting, let's just change to 3 and 3. We can go to 1 to 1, to make it just one giant bin. So mesh result before was like 58% at peak and 95% average was error rate. So most of them were error, essentially. So let's change it to smaller bins. Now the error rate is better. We can, of course, go up in ray counts later on to enhance the accuracy of radiometric accuracy. So now we have pretty good image. Let's go back and do a parametric analysis. So here it says launch parametric analysis utility. What this will do is this will essentially move the angle at which the sun is coming to the earth and simulate how the incident sun or insolation amount of solar energy will change throughout the day. To do that, we have to, let's see, we have to define a couple of things. This might be a little bit advanced, but I want you to just memorize for your own purpose. Just memorize and follow. In your illumination property, if you go to mesh result, make your incident energy as a merit function and click OK. Now your incident, this part became a variable that LightTools can control from inside or outside. Click OK. Click parametric analysis, which is this guy. The window usually is a bit larger. I don't know why it's too small. And here you can select your variable, which is sun source hours, and select the total power of the solar cell as the resulting measuring variable. And in between 0 and 24, we want to have more steps, so we have better view of the graph. And click run. And this will essentially run 12 different simulations and give us, and that will simulate, measure what the incident power is, change the variable, simulate incident power, and plot them. So this is the resulting plot, which makes sense, right? It just shows that there's no sun when it's dark, goes gradually up, peaks around noon, and goes down. So this makes total sense. So this would be the simplest way to kind of look at your solar system and how the energy intensity, energy absorbance changes as a function of time. Just as a side tip, you can double click at this graph, Control C, copy, come here, this is where I practiced, paste. It's going to give you the raw data. So you can plot it yourself or take a derivative, whatever you want. But as you look at the results, not very good, right? This is the actual energy that's hitting the surface of the Earth. Compared to this, what you're getting as a result of the analysis is pretty bad. The reason is because you're not your cell is not facing the sun. And by making your device facing the sun, you're naturally going to get much higher output. But before that, I want to show you another tactic that you can do to improve the energy collection ability of your system. can you guys learn about CPV, concentrated photovoltaics? How people use lenses and lenses and or Fresnel lenses to concentrate energy to boost the power. So we're going to simulate that and see what the difference is between the non-concentrated solar cell energy output and concentrated one. Okay, so zoom out. Before we do that, I'm just going to set everything to like initial variable. Right now, the time is set to too late. Everything seems to be tilted. So we're going to set position sun directly overhead and set tracking system tilt to 0. And I think I have to make a day path. And here the blue line, blue curve, is just representing how the sun goes up and down. Okay, now let's add a concentrator. So what kind of concentrator you guys want to add? Fresnel lens. Fresnel lens obviously is the most popular sort of a concentrator. It's much thinner and lighter than the reflective, bulky lenses. But how would you design a Fresnel lens using LightTools? Two ways. One, you can design Fresnel lens in SolidWorks and import to LightTools. They support pretty well. They support SolidWorks pretty well. Everything that made in SolidWorks can be imported. But luckily, we have another utility library tool called Geometry. And this geometry tool contains a bunch of geometric optics that is sort of a pre-made, or things that can be made with one or two parameters, or a couple of parameters. Within it, there is a Fresnel lenses, our wanted friend. And there are a lot of variables that you can play with later on. But just know that there's this tool to create Fresnel lens, which you can play with to make an optimum concentrator later on your project. So I'll just do the design myself, and you can just watch how I do it to make the Fresnel lens. So I'm gonna choose ideal focus on smooth side and create 2 meter by 2 meter Fresnel lens. And it's important to change your type to extrude to regular. Extrude does one-dimensional focusing. Radial focuses 2. And I want my Fresnel lens to be rectangular. Let's create a lens and see how it looks. Oops. Okay. It has the Fresnel lens at the bottom, but it's not what we wanted. Yeah, this is where the playing with part comes in. We want the thickness to be a little less, right? Right now it's 1 meter thick. We want it to be, say, 0.1 meter thick. And the grooves here are really, really coarse. It's not likely to focus it very well. The reason is because the focal length is too high. We want, okay, oops, some error. I think I can apply change. Oops, again, weird design, right? It's not really the Fresnel lens we wanted to see. I figured that you have to play with this maximum depth and width in order to make it work. So I'm gonna change it to 0.1 and 0.1 and apply change. And now it looks like a Fresnel lens that we are familiar with. But right now it's standing right on top of the solar cell, which, it's not really what we want to. So let's come here again, System Navigator, and find my lens property. And this is where the typing really comes in handy. So, mouse control, we don't do a lot of mouse control in LightTools. I figured it out. I'm gonna put this lens 50 cents above the cell. Is that okay? All right. Set it right there. And since we made our lens 50 cents above the cell, we want to make our focal length also 50 centimeters. The grooves has gotten more finer to create tighter shorter focal length. And if you are wondering if you're actually designing a good Fresnel lens, again, I suggest you to use this NS rays when you're in a process of designing something, right? So I'm gonna just do that. But instead of a fanning ray, I wanna use a grid of two-dimensional rays that are raining down. Oops. I'm gonna change that. What I typically find myself doing is when I create using mouse, I don't really pay attention. Then I come back to this property and then change their property to get really what I want. So I want them to be at 0 and 0 in XY and about 1 meter above. Okay, but I don't want them to have much of an angle. So I change the angle. And now they are coming. So you can see that the focus I'm getting, just by looking at the NS rays, it's not very good. The reason probably, as you would have imagined, is because I'm using ideal focus on the smooth side, which means if I'm focusing something that's coming in and focusing at the smooth side, it's going to focus really well, but not the opposite. So if I change it to ideal focus on fastest side, it actually works really well. So that's sort of a downside of the Fresnel lens. It doesn't work in both ways. It has only one focal. It can be designed to focus in one side really well, but it doesn't guarantee the focus of the other side, lights that's coming from the other side. And another thing that I figured out using this tool is that, let me just change my fan width to 1 meter. Okay, so that it comes at a wider angle. Oops. I want to have more rays coming down. And the location that's maybe a little bit up. Okay. I don't know if this is an error in the LightTools, but somehow if I shoot rays from the smooth side, it only focuses light at the center, but not on the edges. I think it's some sort of a bug. So to deal with that bug, I'm going to essentially flip the Fresnel lens by changing the alpha degree, I think, just flip upside down, so that it actually focuses every ray in the focus. It's not really designed properly, but it actually at least interacts with all the rays that's hitting the lens. Okay. Now we have that. We want to change it back to ideal focus on the smooth side. Take some time. Okay, now it focuses really well. And move. Oops. The Fresnel lens few meter up, so that it focuses well into the cell. Why do you think you're not seeing the light that's hitting at the edges going to the cell? What do you think the reason is?
It's outside the boundary.
Right. So it's the rays that's coming outside of boundary. It doesn't have enough power. The lens itself doesn't have enough power to focus that much of the light. So in that particular case, you can make a design choice to make your lens a little bit smaller, or make your lens a little bit located further away and have longer focal lengths so that they can actually focus all the lights that's hitting the surface. Okay, so now we've designed our concentrator. We can, again, do the parametric analysis. So it's exactly same analysis. We're just doing it with concentrator. Again, come back to solar utility. Open up the parametric analysis tool and add hours. I'm gonna use 12 steps, and I want to measure the power and start. Oops. It's actually pretty cool to look at how the rays are changing as time goes by. Okay, so we don't need to see the feet. What are we seeing? Okay, so the power we've measured is of 3 watts at the peak compared to what we've saw before. Is this the number? I think it is. It's pretty low. Let me try this with 25 steps because I think I actually missed the peak point where the sun is aligned.
Do you know the power of the sun?
Oh yeah, good question. Yes, I do. If you come here, double click on direct sun emittance, there's a radiometric power, and that's the total power your sun is emitting. Okay.
How about the distance?
Distance, you define the distance in the tool, so in the solar tool. In the other option, here the sun distance is defined as 2,000 meters. It's depending on your aim radius, the sun distance is sort of automatically computed. So you don't have to worry too much about distance. So you just define how much of an area you want to shine, and everything's all automatically done. Okay. So you can see it's relatively good around noon, but it drastically goes down. Opinions? Nope. So the problem with concentrator system is that when the angle shifts, the focal point shifts, right? So you're focusing still, but you're focusing at a wrong place. So what comes, concentrated PV always comes with tracking system. That's kind of de facto. There's no, in other words, there's no concentrating system without tracking.
So for the receiver, is it just a point or?
Oh no, receiver can be point, but it is typically a surface.
Surface is uniform surface.
Right. What do you mean a uniform surface?
So I mean, when you're getting the plots, how can you will you calculate how much energy you absorb? Is it just you calculate from the area of the receiver?
Right. So you essentially count the number of rays that's hitting within the receiver area. Of course, you can then look into the scatter plot and see the distribution of the rays. That's how I how I showed that the raster plot represents spatial intensity. But yes, to calculate this number, you are counting all the rays that's hitting the sun. Okay. So let me show you quickly how you can implement the tracking. Okay, just to make it simpler, I'm going to disable my Fresnel lens, hide it, and turn traceability off. So by turning traceability off, it's not anymore interacting with light or rays. I'm also removing grid rays, just hide them. Okay. Come here. What I now do, oops, where's my solar source? By the way, it's okay to turn off the solar source window and turn it on. It will do the same thing. Come here to do tracking option. Okay, here you can turn either one axis or two axis tracking system. I'll just do two axis tracking to optimize the performance. Okay, set tracking system tilt to 0, and let's make everything sort of to initial position. So now the tracking is enabled because we've turned two axis, change our options to no tracking to tracking. But there's just one more thing to do. You have to go to optimization and input window. This is a little fast to follow, so just watch the video again and just follow exactly how I do it. Go to variable, sun source, and click user button 1. It's totally doesn't make sense why I have to do this, but this is just procedure I have to do. Come back here, click OK, and open up parametric analysis again. Pops up. Okay, do the same thing. 25. Run. Look at the results in real time. Oh, my bad. You're supposed to see the cell actually tracking the sun. Let me just make sure that I did it. If I did it right. Okay, tracking. Yep, now enable it. Track to 0, 0, 0, and run again. Okay, it'll take just a few seconds. I think I have to use button 1. Okay. Tracking system, set tracking. Tracking system includes the cells. Okay. And run. This is awkward. 1 second. Just make sure that I'm following the protocol. Okay. Turn everything for now. Okay, we use optimization input again. Use button 1. Okay. Solar tracking. Tracking system. group will be tracked. Okay. Let's see. Come on. Yep. So now this is tracking. Now you can clearly see how the cell moves along the sun direction. And let's do the finer steps and see how the intensity, the measured power differs compared to non-tracking system. So the power clearly is higher at the peak as well as at the non-peak times, where it's generally maintaining pretty high powers throughout. Okay, that's the power of tracking, but of course tracking system cost. So typically people don't use tracking system for regular um, non-concentrated solar panels, but they do with the Fresnel concentrators. So I want to enable my Fresnel lens now, show it. And what I have to do is, so the tracking system, this group is what's going to track following the sun. So I'm going to come here using a group, add my Fresnel lens to the tracking group. By doing so, what I can do now is to track the sun along with the Fresnel lens, okay, to show you how this is moving to track the sun together. Okay, they're moving together to track the sun, concentrate the light on the cell. But notice how this now takes a little bit more time to simulate. That's because now there's another layer of interaction for the rays to go through. Okay. Although, yeah, the power seems to be lower. There must be something I did wrong when I placed my solar Fresnel lens. So this is good kind of analysis tool to make sure that you've done something right or wrong. When I tested it on my own, it actually showed power boost of I think 4 times or so. Of course, the power boost is relevant to the size and how much you're concentrating, concentration ratio, and the size of the cell, and etc. But this is how you do it. This is how you perform the solar concentration as well as solar tracking. Any questions so far? So the result shows that even though it's actually worse when you put a Fresnel lens, for some reason, I probably have put a wrong sort of a Fresnel lens there, or wrong focal lengths, or wrong alignment of some sort. It actually has improved since we didn't have tracking system. So tracking system always helps. It's much more expensive to put, even much more expensive to put compared to even Fresnel lenses. Yeah, I don't think I'll have time to cover my Canula project, but if you guys have any questions on LightTools, please come by to see me. I'll be your resources. But before you come to find me, once you install LightTools, I want you to go to help and go through document library, at least do the introductory tutorials before you come up with too much questions. All right. So they will go through essentially the same examples that I've done and walk you through the details of what each individual functions would do. There's also help menu and this what is this button, which you can click and get the help for. Yeah, I think I have done it. I'm glad that I've done solar concentrator example, because this would be really the core of you guys, the project of the core of your projects in doing solar energy applications. All
Where's
right.
your office?
It's 1444 MEV.
1444.
Yes. All right.
And we can just email you and then set up an appointment if we have
Yes,
questions.
that would be good. Yeah, I usually sit there, but sometimes I might not be there. Just
Okay.
running around. Let me conclude this lecture now. Okay. How do I stop it?